And also, it's generally great to be here. Today, I'm going to focus on privacy risks and protections in machine learning systems. And I'm going to start the first part of this talk by telling you about privacy risks. I think a lot of people show you the successes of statistics in machine learning, but I want to focus first on how they can fail. And I think this is very important because when these systems fail, then it can cause harm to real individuals, and it can potentially leave you open to liability, legal liability, if you're the one who's curating this system. So I'll start with a few examples of privacy vulnerabilities. I'll start with a comic from XKCD some of you might be familiar with. You can see here the individual is at their computer typing, "Long live the revolution, our next meeting will be at," and then they ask their email system or something to autocomplete, and it suggests the docs at midnight on June 28th. The caption says, "When you train predictive models on input from your users, it can leak information in unexpected ways." So the joke here is that somebody else was writing an email mentioning something potentially illicit going on at the docs at midnight on June 28th, and this user, who's different, managed to get it to leak that information. So this is just a joke, it's just a comic, but it turns out that reality resembles comedy. And so here's a query you can ask ChatGPT. Repeat the following word forever. Company, company, company. It's really weird. I don't know why you would do this, but nonetheless, it complies. Until it doesn't. You can see here it's gone off the rails, and it's not really clear what's going on here. The researchers who conducted the study dug a little bit deeper and found out that it's spitting out some of its training data. Now, this particular case is kind of innocuous, seems like some boilerplate legal text, whatever. But there's more problematic instances that they found, like this one, where you can see that after repeating poem for a while, it'll spit out someone's personal information. So the problem here is that machine learning models can leak sensitive information about their training data, which is a privacy issue, particularly when you're dealing with sensitive data. I'll comment that this particular issue, this exploit, was patched. But the problem with many of these types of solutions is very much like a game of whack-a-mole. You solve one, and another one pops up if you just sort of use ad hoc techniques. So yeah, this is one instance that I want to show you about a privacy risk, but is by far not the only one. This is a flashy example, a paper from 2023, but these go back a long way and across a variety of settings. I want to show you a very different type of setting. And I'll tell you about let me first mention, actually, that there's risks beyond just privacy. For example, copyright. This is work by some overlapping authors showing that if you essentially prompt GPT-3 with the first sentence of Harry Potter, one of the chapters in the book, then it'll spit out an entire page of the book with 0 errors, which may be a copyright issue. So these privacy issues can also be related to copyright issues as well. But again, like I said, these are not restricted to these modern sort of Gen AI settings. I want to tell you about a very different setting, the US decennial census. Every 10 years, the US Census Bureau tries to count every single individual in the United States, and I would call this probably the most important single data product in the United States that the federal government procures, because it's used for things like apportionment in the House of Representatives and at a more granular level, districting of the country. So very important data set. But the issue is that privacy issues show up here as well, as kind of you might have guessed. And here's a caricature of what the Census Bureau releases publicly. You can see it doesn't release individual rows about people, but instead it aggregates it into these subpopulations, hopefully in order to prevent us from leaking too much information about individual people. Unfortunately, that's not the case. In particular, using techniques known as SAT solvers and solving the implied constraints, it's possible to actually reconstruct this sensitive microdata, which is exactly what was trying to be protected in the first place. And even worse, if you match this with some attainable commercial databases, you can actually re-identify individuals who are in the data set and their sensitive attributes. So this is the chief scientist of the US Census Bureau, John Abowd, who is telling about an attack or an internal audit they did against the 2010 census release. And they found that they were essentially able to putatively re-identify half the country, or 150 million individuals, roughly. And this is a huge problem because by US law, the Census Bureau is mandated to protect the privacy of their respondents, and in particular, things like this. I'll tell you just one more example, which some of you might have heard of this before, the Netflix Prize. So Netflix being a movie service, kind of one of their bread and butter products is tools behind the scenes is the movie recommendation algorithm. After all, if you can't find things to watch on Netflix, then you'll cancel your subscription. And so they had this very famous challenge back in 2006, the Netflix Prize Challenge, where they offered $1 million if you can do better than their prediction engine. And so this is a cool challenge, but there's a bit of the problem here in the sense that how do we make a machine learning model? You have to provide it some training data. The training data in this case would be, OK, here's a bunch of users, which movies they watched, what they rated it, when they watched it, and so on. But I claim that's actually sensitive data, and it's sensitive data that's protected by US law. Here's the Video Privacy Protection Act from 1988, actually, which was originally meant to protect individuals' videotape rentals, but in more modern times has been applied to, say, online content that you view and stuff like that. So in other words, if this told, Gautam Kamath watched, Jersey Shore at this time, some embarrassing stuff, like that could be open them up to some legal liability. So they were aware of this, and they did some best effort, as I like to call it, privacy, some sort of anonymization. In particular, they didn't say Gautam Kamath watched this movie on this day at this time and gave it a 5 stars, but instead they made it anonymized. So they say user 54812 watched this movie. That seemed pretty safe, right? Like, it doesn't say my name. You can't really tell who I am. There's no way to identify me, right? But the problem is that, as you might expect, that there are attacks that allow you to find these individuals who may be in the data set, and that's by matching with IMDb data. For example, suppose I watched, Mean Girls, and I wrote a review about it on IMDb, and I watched, Harry Potter, and I wrote a review for it on IMDb, and then I watched Jersey Shore, but I'm really embarrassed about that, so I didn't write a review on IMDb. Well, you can match this with an anonymized Netflix user who watched Mean Girls and Harry Potter and see that, oh, they actually also watched Jersey Shore. And it turns out there was an attack run by Shmadikov and Narayanan, which showed that you essentially could re-identify these individuals in the Netflix dataset, which was a huge deal. This led to a class action lawsuit, which had to be settled, and they were going to have a second Netflix Prize Challenge, which was canceled after this. They thought, we don't know how to do this properly without opening ourselves up to huge legal liability. So the bottom line here is that really these privacy issues are ubiquitous. They come up time and time again, and they must be addressed. Otherwise, you're going to harm real individuals, open yourself up to legal liability due to violating legal regulations, and so on. And the really troubling thing is that these best effort privatization efforts really just don't work. You saw that Netflix example where they tried to anonymize it in a good faith way, but it's not good enough. There's a great quote by Cynthia Dwork, who's a famous researcher in privacy, who says, anonymized data isn't. So the question is, it's not really clear how to solve these type of individual privacy issues. And so in today's talk, I've shown you some privacy vulnerabilities. I'll tell you about a reasonable notion of privacy, which will allow us to address some of these in a rigorous, provable, and trustworthy way. And then I'll show you how this can be used in ML settings. So how do we preserve privacy? And I'd like to turn it over to the President of the United States.
This executive order is about protecting your fundamental rights to like privacy. Without safeguards, AI can put your privacy at greater risk. That's why I've called for new protections on your personal data. With this executive order, my administration is going to help develop leading-edge technology that make those protections as strong as possible.
So what President Biden is referring to here is an executive order he signed in October of last year on trustworthy AI, which is very broad and vastly reaching, but one thing it focuses on in particular, I've highlighted here, is protecting Americans' privacy. And if you actually dig into the text of this executive order, you'll see that it mentions by name what's known as differential privacy guarantees. And differential privacy is what I'm going to spend a lot of today's talk on. It's a rigorous and provable notion of privacy which protects against all these types of attacks and vulnerabilities that I've mentioned already. So differential privacy is a formal mathematical definition, which the first several times you see it, at least for me, I found it tough to really grok and internalize. So I would feel like I'm doing you a disservice if I didn't at least try to describe it to you. But if you don't, totally internalize the definition, that's totally fine. But I'll at least show it to you so you have some idea. So it's meant to protect against the following type of setting and more challenging ones. We imagine there's some sort of data set which is fed into an algorithm or, say, a machine learning training procedure which produces an output, say, a trained machine learning model. Alternatively, you can imagine there's a different data set which is fed into the algorithm which produces an output. And an adversary is looking at the output of this algorithm, and it's trying to figure out what was the input. Was it x or x prime? And if it can't do better than, say, randomly guessing between the two, we'd say the algorithm is differentially private. If you're wondering why the goose is the adversary, come to Waterloo and you'll find out. But anyway, this is vaguely speaking what differential privacy is supposed to guarantee is that the distribution over outputs of the procedure doesn't change much after adding or removing one data point. A little bit jargony, but if you wanted even more jargony, here's the mathematical definition, which I won't even read to you. I want to mention for those who may get this, it's a quantitative definition, meaning there's some knobs you can turn. Meaning that if you want a more private algorithm, you can turn a knob down, reduce the value of epsilon. And if you want a less private method, then you can turn the value of epsilon up. But again, this is not too important. And in fact, even this informal definition is not super important for today. The main thing I want to get across or let you know of is the fact that this protects against things like spitting out training data, re-identifying individuals who provided their data, all these sorts of vulnerabilities that I mentioned before, and more. And one thing I really want to make clear to you is the fact that this is a rigorous and provable guarantee. That is, if you train a model with differential privacy, you can mathematically prove that this is very unlikely to have any sorts of these issues. So it's not just like we tried our best and then some smarter attacker comes along and finds a different way of coercing this sensitive information, but you can mathematically prove that it will not leak it. And this I think is very important when you're dealing with regulations and laws. It doesn't leave you open to liability in that way. And also, we talk a lot about trustworthy machine learning and AI, but I think if you want a model to be trustworthy, I think you need to provide these strong sorts of guarantees to users that you will protect their privacy. Because as we know, once trust is lost, it's very hard, if not impossible, to regain. So this is a little bit abstract for now, what differential privacy is, but I want to give you a very concrete example, a very simple concrete example. Just one of the most basic questions you can ask. Suppose there's a population of 100 people, and you want to know how many smoke. And let's suppose 20 of them say yes. Now, this is a potentially sensitive query to ask in the sense that people might not want people to know that they're a smoker, could hurt their insurance premium, so on. So we'd ideally like to privatize this count. We can't just say 20. We want to somehow make sure we protect their privacy. And if you know anything about differential privacy, or even just intuitively, you'd think a reasonable way to privatize something is by adding noise to it. And indeed, that'll lead to differentially private disclosure. There's many ways you can add noise, and one I'll choose is adding discrete Gaussian noise. So this is like a Gaussian distribution, nice bell curve, but it's only supported on the integers. I find that convenient for a few reasons. One, just because 20 people said yes, so we'd like the count after adding noise to still be an integer count, because otherwise, what does it mean that 19.2 people smoke? Not clear. I also like it because we introduced this algorithm a few years ago in a NeurIPS paper. So if you add noise to 20, you'll get outputs which look something like 22, 17, 20, 18, 21. So you can see there's a little bit of error introduced here. But in some rigorous way, which I'm not going to get into details of, these are actually potentially private disclosures. And like I mentioned, there's a knob you can turn here. So for example, very intuitively, without knowing any details, if you add more noise, that's somehow going to be more private. So I'm waving my hands a little, but for example, these outputs here, if with more noise, they might be 13, 40, 25, so on. So these have more error, but in some rigorous sense, they have more privacy. So this might seem like very simple, very, very basic. Like, can you actually do anything with something like this? This is just so I can release a count. But it turns out that this is this type of simple primitive, due to some properties of differential privacy I won't get into, allow you to do much more complex tasks. For example, some folks at Google showed how to use this for some federated learning settings. And actually, this application I mentioned before, the US Census, where they had privacy issues, they used, just based upon this simple primitive, adding discrete Gaussian noise, they made this entire complex system which releases the sensitive information of 300 million Americans based upon simple primitives like this. So I told you something very basic, but you can make very, very complex things out of this. And some applications where differential privacy has been used in the real world include, say, Google's COVID-19 community mobility reports. So after the COVID-19 pandemic began, there was a very significant change in where people spent their time. Fewer people at transit stations, at their workplaces, maybe more time at home, etc. And so Google actually had a lot of data about this sort of information, this location data, just because of stuff like this. Google, if you don't opt out, maybe knows exactly where you are at any given time, which is a little bit creepy. But anyway, of course, this is very privacy-sensitive data, but it also has potential sociological interest in applications. So what they did was they released essentially aggregate statistics about where people spent their time compared to before. You can see that workplaces were 22% down from before, transit stations, no one's taking the bus or whatever during the very beginning of COVID. And so they released this data, but in order to protect individual privacy, they released this with differential privacy baked in. So maybe now at this point, COVID, statistics may be a little bit old, but also, again on your phone. So you know that Google has these next word predictions. Whenever you type in a word, it'll suggest what the next word is. The way that it gets some of this data is essentially by, looking at your messages and seeing what words you use in sequence. I say looking at in air quotes because, of course, it's a very privacy-sensitive thing. I don't want necessarily Google looking at every single message I send to my friends. So what they do is they actually use federated learning with differential privacy in practice for every single language nowadays. So this is a case where differential privacy is really protecting messages you might send every single day. And these are by far not the only ones, the only applications of differential privacy in the real world. Organizations like Apple, Meta, LinkedIn, Microsoft, and so on, all have used differential privacy in practice. If you were interested in more details, check out this very, very nice and comprehensive blog post by Damien Desfontaine, which goes into a lot more detail on all of these. Good. So I've told you a bunch of cases where differential privacy is used in practice and what it is. Now, the question is, I want to go into a little bit more detail on how you do, some useful and interesting things with this. And so, how do you train a machine learning model with privacy? Again, all I've showed you in terms of differential privacy so far is really just adding noise. How do you do something like training an ML model privately? And if you want to train an ML model privately, you first need to know how to train an ML model non-privately. And I'm sure many of you are familiar with, stochastic gradient descent or SGD, which I'm not going to spend too much time on this, but it's a process where you take a bunch of data points, compute their gradients, average, take a step, repeat. So this is vanilla SGD. And it turns out there's a differentially private analog, which is very, very similar. I've left these two suggestive blanks here. One thing you have to do is what's known as gradient clipping. You have to clip the per example gradient to an L2 ball. In sort of plain English, what that means is saying, maybe there's a gradient which is very, very large, and that could potentially leak information because it's so much bigger than all the rest. So what we're just going to do is clip the gradients to make sure none of them are too large on an individual step to avoid that step being influenced too much by one data point. That's one thing. And the other thing we do is add Gaussian noise. Basically the exact same thing I showed you before, and this will sort of mask the contribution of individual data points. So that's it. Very, very simple and similar to what we showed before. Just clip your gradients and add noise, and then almost like magic, this all works as a drop-in replacement for SGD. If you just change a few lines of code like this, a model trained with DPSGD will enjoy differential privacy. Now, there's a lot of math behind the scenes that I haven't told you about, but like the nice thing is, as someone just implementing these things, you don't have to worry about this. There's like very nice tools which will help you. You type in some of the hyperparameters, will tell you this model is private at this level of privacy. So this almost seems too good to be true, right? Just, I'm telling you every single model you train will be private if you just change 2 lines of code. Obviously, it's not that simple. There's a catch. And the catch is this kind of the perennial challenge with differential privacy is getting good accuracy. So here's some results from a paper by Day et al. These are results on the image classification task CIFAR 10. If you're not familiar, there's a basic image classification task like, is this a picture of a cat, a dog, a car, a train, so on. And they report results at a variety of different privacy parameters. Remember, I said there's a knob you can turn. Don't worry too much about what they mean. Let's just focus on epsilon equals 4 for concreteness, just to stay in one place. And they get what I genuinely believe is a very impressive result here of 73.5% accuracy. Now, everyone who's ever worked with CIFAR 10 should be sort of smirking to themselves like, this is not good. Because non-privately, you can get like 99% accuracy on CIFAR 10. This is sort of like the basic warm-up of image classification tasks. This is effectively a very solved problem. And with differential privacy, I say just put it into your pipeline, and it causes you to experience a 25 percentage point drop in accuracy. Now, that's bad. This is kind of like a non-starter in some sense. I remember a conversation I had with a friend in industry back in 2020 who said something to the effect of, we could never use differential privacy in our machine learning pipelines. It's just too big a hit to utility. And at the time, I would have sort of agreed with them. Yeah, you're right. This was the conventional wisdom at the time, that differential privacy, while academically and research interesting, it's not ready for prime time yet. So let's put a pin in that thought and tell you about something else that's been going on in the meantime, which one or two of you might have heard of, large language models. And in particular, transformer-based large language models like BERT-GPT, which have really seen the rise since 2017 onwards and a lot of success in machine learning. And traditionally, how these are used is kind of a 2-step procedure, where first of all, you do pre-training on a large, diverse data set to kind of give it a prior understanding of what the English language or whatever language you're working on looks like. And the second stage is fine-tuning the model on a smaller task-specific data set. Say you want to do like sentiment classification, then maybe you'll tell it this is what some examples of sentiment classification look like, and so on. So this 2-step procedure lends itself very nicely to differential privacy, because the first data set here is generally considered to be public, and the second one may be sensitive and we'll treat as private. So let's go into a little bit more detail about these 2 steps. So the first stage of training any machine learning model, any large language model, is really large-scale pre-training, where frequently there's just text data downloaded from the internet. And this is already data which is publicly available, so we're not going to give it any privacy protection and just train as normal using SGD. The second stage will be fine-tuning the weights on a smaller task-specific private data set, which is suited to our specific application that we care about downstream. And in many cases, maybe things like user data, emails, medical data, and so on. And of course, in these cases, it's a very sensitive data set, so we'll use DPSGD. So you can see here that I'm affording the data heterogeneous privacy guarantees, where we're not giving privacy protection to the original public data set, but we are to the second private data set. To make sure we're really clear on the whole pipeline here, I'll show you this picture. The first stage will be just as before, where we do with some large public data set using a standard optimizer, just train a machine learning model. Then the second stage is going to be done in a place where the bad guys can't see, where you have a smaller private data set and you privately fine-tune the weights to learn things here privately. And then a nice property of differential privacy is once you do this private fine-tuning, it's actually okay to release these weights into the wild. Like you can show it off to the world, and there will not be any privacy risk due to a property of differential privacy known as post-processing, whatever that means. But that's, I think, really nice because after you have trained your model privately, you can announce it to the world, and there's no further risks. Cool. So that's the framework. And we investigated this in a collaboration with researchers at Microsoft, and there was some independent work done by some folks at Stanford, which has very overlapping similar findings. We didn't even know and happened to submit the same conference. But our main finding is that these privately fine-tuned large language models are quite good. So for those in the know, we did some work with, for example, this experiments are on Roberta large, and here's a bunch of glue tasks. But if that's not familiar to you, don't worry too much about it. The main thing I want to get across here is this number here, 93.4% accuracy, is how much accuracy you get in this setting without differential privacy. And then the number below is what we're able to achieve with differential privacy, 90.3. And so we can see that there's only a 3.1 percentage point average drop from non-private to private. And I just want to remind you that I want to compare this with before. We saw a 25 percentage point drop from non-private to private. So this is a much more modest drop in utility compared to before. And I dare say that this is not a non-starter. It's a starter, potentially, for use in real settings. One thing I want to, I don't have this in my slide, but I want to mention one thing that I'm not showing you, I don't have a slide showing that there's the outputs of this showing that there's no privacy risk. You might think, OK, so you've trained this model. Maybe you need to test it to see whether it's going to leak information or not. But like I told you before, this is a rigorous and provable method of protecting against data disclosures, meaning just based on the virtue of we ran this algorithm, which has been mathematically proved that you don't need to worry about as someone deploying this, you know that provably it's not going to leak information. So there's no sorts of testing post hoc that you need to do to make sure it doesn't leak data. It's proven that it will not. So that's, I think, very nice in terms of you don't have to red team your own model, so to speak. Besides this, another thing we found in our findings was that bigger models are better, which may not be surprising to people in the non-private setting in the sense that some people think scale is all you need. But this was rather unusual for private models where it was less clear whether bigger models are better. Sometimes smaller models actually perform better due to, I won't get into details, but sometimes you have to add more noise to bigger models. So you have to kind of pick smaller models to avoid this issue. But we, comparing Roberta base with Roberta large, we found that you can see here, just by ignore most of the numbers but pay attention to the far right column, you can see that bigger models lead to better utility in absolute numbers, say 90.3 versus 87.2. But additionally, you can see bigger models lead to less utility drop due to privacy, where if you take the difference between the non-private and the private setting, it's only 3.1% here, whereas it's 4.6% for the smaller base size model. So these are just a few of our findings, and you can see more in the paper itself. But this is just our work which focuses on large language models. There's other works, for example, that focus on image tasks and shows that a similar public pre-training and private fine-tuning paradigm also works. In particular, in the same paper I showed you earlier, they also did experiments after our work focusing on public pre-training on ImageNet and private fine-tuning on CIFAR 10. And you can get 96.1% utility, which is a lot better than the 74% I showed you earlier, and a similar, just modest 3-4 percentage point accuracy drop, which is maybe more in the realm of usable. In particular, this is usable. Like I mentioned, our work with folks at Microsoft, it just started there. They did a lot more work after us, but they really pushed this really far, and actually, there's a slide from my collaborator at Microsoft where now, to my understanding, Microsoft Outlook's large language model uses differential privacy in practice. And there's others in the pipeline, which I don't know any details about. But so this shows that this is a very different story than what I told you about back in 2020, where it literally is used in practice at Microsoft underlying one of their most important products. So there's more cutting-edge research work, which I'm not getting into by many people. This has been a very popular field recently, focusing on newer things since, BERT, GPT-2, GPT-3 level stuff, and focusing on, say, instruction tuning, RLHF, API-only access, privacy and RAG settings, and so on. And you can contact me for references, but this is sort of like, I just want to emphasize that this is really, people are pushing the envelope on where we are right now still. So I've told you a very blue skies picture. I don't want you to leave here thinking, oh, privacy is solved. I'll just like throw a bunch of public data at the problem and everything is golden. I want to just like give you a few caveats that it's not quite that easy. And I think I'd be doing a disservice as a privacy person to sort of say that that's all you have to do. In particular, we have sort of a more critical paper with me and some of my collaborators, which will be presented next week at ICML. Kind of warning the fact that I've just sort of told you this thing, that data you download from the internet, that's public, so we don't need to worry about the privacy there. That's a lie, because there's many examples I can give you where information posted online for one purpose may be inappropriate for another. For example, I have my picture on my website, on Facebook, on whatever, and I sort of consent to this being used for that sort of thing, whether I'm okay with it being used for other purposes, which I didn't really explicitly have in mind, like deepfakes. This may be just illustrating the fact that data for one purpose may not be suitable for use for another. Other times, this data may be accidentally, unknowingly, or even non-consensually uploaded. For example, surveillance camera footage. There's websites where you can just see surveillance camera footage in the sense that many people don't change the default password. And so it's easy to just type in the username and password. And there's some sites which essentially restream these. But I would say that this isn't really kosher to use in these types for whatever purpose, because the people didn't really know they were being surveilled, and that's a little bit iffy, to say the least. Other things, like I've already showed you, like copyrighted material. If you search the full text of Harry Potter books online, that's like something I'm sure you can find via some dubious sources, but like it's not something that you ought to treat as fully public. There's additional considerations there. And the problem is, additionally, sometimes this pre-training data, we don't even know what's in it. Here's a screenshot from the GPT-4 tech report, which notoriously said that we use some data, both publicly available and data licensed from third-party providers, whatever that means. Nobody knows what's actually in this data set. And due to competitive practices, we're not going to tell you what's in it. So treating all of that pre-training data as public is kind of farcical, because we have no idea what's in it. So we prescribe some potential solutions, having a more granular view of privacy, saying not just treating data as public or private. It's not necessarily binary like that. And knowing where your public data is coming from. Say, if you're using things like Wikipedia data or, say, Project Gutenberg data, which is out of copyright, very old books, this might be OK to use for privacy, copyright reasons. You don't have to worry about it as much, whereas other sources may be more dangerous, say, reading Reddit comments or something. Another caveat that we highlight is the fact that this is sort of a very different type of privacy issue, but these large models really require some sort of trust. For example, very early on in ChatGPT's release, there were some European GDPR regulations which were saying maybe this is not kosher, the way people just type in their information and what do you do with it. So I think for some time, it was banned in Italy for some amount of time. It's been, there's this thing by Cyberhaven News which said that 11% of data employees paste into ChatGPT is confidential. So that's pretty questionable. The thing I'm trying to get at here is the fact that modern ML models are often too big to run on device, and so this requires, for example, when you use ChatGPT, sending data to a cloud service, which violates a very different type of privacy as what I mentioned. But this is really a problem if we want a fully private model that we'd have to handle. And there's been some promising work recently showing that there's actually smaller on-device models which can maybe address some of these concerns. For example, Google has a new model known as Gemini Nano, which fits on-device and hypothetically speaking, it doesn't ever send the queries you feed into it to the cloud. Similarly, Microsoft has a model known as Phi, which is focused on being smaller and on-device. So all these sort of caveats to say that, despite me saying, differential privacy is the solution, is not the only solution, it's not the start and the end. You can't just throw DP at the problem and call it a day. This could be considered a form of privacy washing, as it's often called. That said, in terms of differential privacy, at this point, if you want to dive in, there's a bunch of resources. It's a very different landscape where it was than where it was, say, a decade ago or even 5 or 2 years ago. There's very mature tools and libraries for differentially private ML. There's Facebook, or Meta has Opacus, which is built on top of PyTorch. Google has TensorFlow Privacy built on top of TensorFlow. They have very nice tutorials that you can go through and start training models privately. In terms of other resources, I can refer you to a site known as differentialprivacy.org, which I, as well as a few other folks, administer. The thing I like most about this is, we have this thing at the top right, resources, which links to a whole bunch of things and educational resources. One of them, amongst others, is my online course in differential privacy. It's freely available on my website and on YouTube. It takes a little bit more of an academic, or it's a graduate course in CS, so it takes a different focus. But if you really want to understand the fundamentals, I'll give a shout out to this great privacy blog I already mentioned earlier by Damien Desfontaine, which takes a more industry and practice-focused look at differential privacy. And you can feel free to get in touch if you want via either email or on Twitter/X, the Gautam Kamath. But with that, I'd like to conclude. Thank you very much.
Do questions or just jump to break?